All right, so again, the exam will be moved. We'll explain more details of the exam on Tuesday next week. But again, if you have any issues with thinking you'll have enough time on Thursday, just reach out to me and we'll figure that out. Okay, so on to some homework questions. So just a reminder, what we did last class, sort of to move into this. So last class we did a few things. Most importantly, we introduced integration by parts, which is extremely important. And we also discussed certain types of trig integrals. So when I use the word trig in front of integrals, what I mean is we're asking you to integrate trigonometric functions. And so the homework that you're currently working on, hopefully, is homework 3, and there's undoubtedly going to be some questions because these are challenging ones. And the one that was first asked was 1L. So let's talk about it. So give me a marker. So if I give you this particular integral, what should your thought process be? Well, so we have sine to the third power times cosine to the second power. We want to integrate this. So let's call this number 1. Now, here's the way your mind has to work. Integration, as I've pointed out numerous times now, is a skill. It is an acquired skill that requires lots of practice. So what makes integration different than taking a derivative is that the derivative is very procedural. If I give you a function and you know the proper rules, then it is very algorithmic. It's very recipe-based. It's very procedural. You just do this, this, and this, and you're done. Integration, you might think, would be very similar because integrals and derivatives are inverse sort of operations. But the fact of the matter is integration is much more challenging because there is no direct procedure. It's a skill that is only honed through lots and lots of practice. And your strategies are very much, again, there's no systematic way of doing it like there is with derivatives. Now, the more you practice, the more certain themes you'll see and the more sort of systematic things seem to pop up, but there is no general rule of thumb for how to integrate every particular function. In fact, what's quite interesting is we touch on it slightly in this course. There are actually functions out there that you cannot write its antiderivative down, or you can't quote unquote integrate it, as it were. So we'll touch on that, you know, in due time. But it's worth understanding that you could be really good at differentiating, but integration is a different beast. It requires a lot more practice and a lot more experience before you really start to make sense of any of it. With that in mind, what do I think about when I am given an integral? The first thing I think about is I ask myself, can I classify it into a certain type where then I can narrow down what my strategies might be? So a good metaphor for this, or analogy, whatever you want to say, is like, imagine you are a surgeon in the emergency room, or and you know, some patient comes in and they're not breathing or something, or they're bleeding. You don't just start like chopping body parts off or cutting them open and to fix them, right? You have to diagnose what the problem is. you have to figure out what the issue might be before you go about figuring out how you're going to correct it or fix the patient. Similarly, if I own an auto mechanic shop, if someone comes in and their light and their check engine light's on, you know, I don't just put the car in the air and take the wheels off and then drop the engine out of it, right? That would be very impractical. What I do as a professional is I diagnose the problem. I say, okay, what do I think the issue is? And then once I either know what the issue is or I think I have an idea, then I've narrowed down my options for how I might fix it. And integration is very much the same. You have to look at these things as each integral is its own beast. And you need to figure out a way to diagnose what sort of type of integral it might be and how you might solve it. For example, I think we can all say with a pretty confident voice that when you look at this, it doesn't look like there's going to be a simple formula, right? This doesn't look like a real simple one like we talked about in Calculus 1. And then the next thing you note is you might say, okay, well, I see the two functions in there. I see the product, so maybe the integration by parts formula would be useful. And it could be. But what I see and what I taught you to see is when you look at a integral that has sines and cosines, you look at the powers. And what I see is I see two powers. I see a 3, which is an odd number. And then I see a power 2, which is even. And then I remember, because I've practiced this, that if I have at least one odd guy, the strategy that I like to employ is to separate that odd guy and then use a substitution. So here's the key idea. It's to take advantage of that odd power. So here's how I would do it. Let me get a good color here. So here's the key idea for me, or the key thing to note. One power is odd, and that suggests the following strategy. So what I'm going to do is I'm going to take my original integral, and I am going to take the odd power and write it as even power plus 1. So in that case, it's sine squared. And then I'm going to write the power 1 part over here. So the first thing is you need to understand that what I wrote is legal. It makes sense. I didn't do anything. I'm just writing the same thing in two different ways. Now look, your intuition might say, okay, I see sines and cosines, so why doesn't a u sub work? Because I know that the derivative of sine is cosine, so it seems to me like a u sub might make this ugly thing go away. Now, it turns out that it will, but we have to set it up properly. So we have to put it in the correct form so that the substitution works. This is not always so obvious. So one way that this works, and maybe you have to come at this through trial and error, maybe you don't. One way that will work is you now take your even power of the sine and you replace it with 1 minus cosine squared. I am using the basic trig identity of sine squared plus cosine squared equals 1. Now, of course, your thought initially is going to be, well, how would I know to do that? Well, you wouldn't. That's why we have classes and books and videos and teachers. it would probably take you a long time to figure this out if someone didn't show you or give you a nudge in the correct direction. But the beauty of this is when I write it this way is now there is an obvious substitution. Now, of course, you're going to say, well, it's not obvious to me. And I'm going to say, of course it's not, because you're a beginner. You're a learner. You're an amateur. If it was obvious to you, you wouldn't need to be in the class. What's important, though, is that you work to understand why it is obvious in hindsight. That's where the learning comes from. See, a big mistake that many of you will do is you'll just take these integrals and you'll go to the internet, which will do them for you, and you'll plug them in the Wolfram or Mathway or whatever app you have. And then essentially all you're being able to do is get a 10 out of 10 on a homework, which what good is that 5 years from now? What good is that 10 years from now? If you want a true learning experience, what you should really try to do is to understand what it is we're doing from a logical standpoint and why. Now, that's the hard thing to do. That's the hard part. It's easy to go get the answer from the back of the book or from the internet or from a tutor. The hard thing is to understand what the thought process is and why. But that's also the learning experience there. Okay, so if I set it up like this, then when I look at this, I say, well, geez, if I just replace cosine with another letter, things are going to simplify quite easily. So if I do that, if I set, I'm going to choose y. If I set y equal to the cosine of x, then my dy dx is negative the sine of x, which means that dy with a minus sign is the same thing as sine of x dx. So, of course, you might say, well, why did you write it like that? And again, that is my personal preference. But if you flip back a page, what you'll notice is then I am accounting for everything that's in this integral. Here's my sine x dx. Here's my cosine. Here's my cosine. And then the integral simplifies immediately to minus, I have a minus sign floating around, 1 minus y squared times y squared dy. And then this is nothing more than a polynomial, which everybody loves to integrate if they have to integrate because it's very, very easy. So I'll rewrite it like this so that that minus sign is not floating around there. So we're going to give you a moment to catch up. And if you have a question or a comment, please ask. Even when I say things are obvious and I use words like that, I don't mean that in a way. I want you to think it's obvious in hindsight. And I want you to remind yourself that this is not an easy thing to learn. Does anybody have a question about this piece? I'm not done yet. I've only rewritten my integral from one form which I couldn't integrate to a form in which I can now integrate. Technically, since we learned this. So how do you integrate to the fourth power? This is 1/5 y to the 5th minus 1/3 y to the 3rd plus our arbitrary constant. And then all that remains is that we replace y with its corresponding x, which is cosine. Oops. and we have officially integrated sine cubed cosine squared. There's a few comments we have to make about this before we go anywhere. But if you have a question, please let me know. We good? Michelle, I pick on you. You asked. Are you good with this? Yay, nay? Anybody else want to talk about this? Want to talk about life? It's nice. Is it sunny? Let's check. Oh, it's sunny out. We're stuck here. What a terrible thing. Any other questions on this homework do you guys want to talk about? Actually, before we do that, let me say this. What happens is, and let me show you one of the issues that you might run into, and you might think you're doing things wrong. For example, you might have done this problem and got an answer that doesn't look like mine, and you might think you're wrong. Or maybe you went to the internet to Wolfram or something. Let's see what Wolfram gets. Let's do that. That's always fun. And you might think you're wrong, but that's very rarely well, I shouldn't say it's rarely the case. You guys are often wrong. That's so what happens is when software does this for you, they often are programmed to do things a little different than human minds work. And so often they might employ different tools to integrate, and they almost, and whoever programmed them, like Wolfram might have something where they're like, oh, okay, I don't like this trig identity, I like something else. So for example, if I go to Wolfram, and I ask Wolfram to integrate, what was it, sine cubed, cosine squared. And it's Wolfram's pretty good. They don't mess around. They're like a Google. Oh, see, it's mad because I didn't put a space there. So let's put our X here and put a space here. And I think they'll catch up to us now. Yeah, they do. And you'll see that they get an answer that does not look like ours. And of course, the first thing you, the student's going to say is, well, I did it wrong then, or O'Grady don't know what the hell he's doing. See, the difference between you and me is when I was in trig class, I paid attention. And what I could show you is that answer that Wolfram has is the exact same thing that I have. It's just written in two different ways. Wolfram is going to choose to factor things a certain way. It's going to choose to use certain trig identities. But the answer that you see right now on Wolfram is exactly the same thing as what I got. It's just two ways to write the same thing. You guys should verify that for your own, confidence. So again, I am not wrong. Wolfram is not wrong. We are both writing the same thing two different ways. Now, I believe if here's some alternate forms. They wrote it like this, and then they're going to start scaring you down here. Woo! Then you have all this. Oh, by the way, here's some advice. When you go to a Wolfram or any web page and you write something down and you copy it, don't copy something down unless you understand what it means. Like, I find a very hard time thinking that any of you in this class right now know what this one thing means or what this means. Yet you would be so happy to write it down on a test. You shouldn't take things if you don't understand what they mean. That being said, you should also use websites like Wolfram as an opportunity to learn things you don't know. So let me make the moral of this little interjection. There's nothing wrong with using technology. There's nothing wrong with using software, but you gotta understand what you're doing and what you're writing down. And also, you have to keep in mind that just because your answer varies from what you find on the computer, that doesn't mean you're wrong. It just means you might be writing your answer in a different form. Hopefully that makes sense. And I feel obligated to talk about Wolfram because it'd be stupid of me. I shouldn't use the word stupid, but it would be foolish of me to assume that some of you don't use things like Wolfram. Why wouldn't you? It's an amazing tool. And if you pay them money, they'll show you everything, right? See, they did the same thing I did. Look, break it up like this, and then look, it's the same thing. It's like they cheated from me. All right, I kid. All right, any questions about this problem? Any other questions about any of these integrals on homework? What is this, 3? Homework 3? Yeah. Going once, going twice. What's nice is some of you probably were thinking like, man, I didn't get the same thing Wolfram had, and now you're all sad. But now you know maybe you are right. So that happens every semester. Students think they're doing it wrong. All right, so this is a all right, so I take your silence as no more questions, that we can move on. Sweet. All right, so then let's see where that leads us. So next page. So our next strategy / technique for integration deals with integrals involving what we call certain algebraic expressions such as you might have something like the square root of 1 minus x squared, or the square root of x squared minus 9. So first off, I want you to, the first thing you should be thinking about right now is why would some integrals have these things, but then it doesn't take long for you to think about the geometric and the practical applications we talked about before. With arc length has square roots in them, right? What else has square roots in them? The surface area integrals had square roots. So things that have creatures like this arise naturally, and we would like to maybe think about how we could integrate them. Okay, so first off, one of the things that I kind of think about, and I don't know if it's because of the math teachers I had when I was in high school, but whenever I see something like that first square root, that just screams circle to me. It just does. It might not to you, but it does to me. And anytime I think about circles, I think about that circles and triangles are very much related. You might not think that, and that's fine, but they are. Take any point on a circle and then draw a line straight down to, if you take a circle centered at the origin, and you draw a line to the x-axis, you can create a right triangle. And then there's a very nice relationship between that right triangle and the sine and cosine of its angles and that circle. So I'm going to explain it more in detail what I mean by that. But I don't want you to think what we're about to do doesn't have motivation or doesn't have some sort of, you know, how do you say it? Doesn't have some sort of context. These things that we're about to do, they're not magic, and they work because the logic works out. But the motivation for why they work is because of the geometric considerations. So let's look at an investigation. We're going to do this once, and we're going to help. Hopefully, you'll quite understand, or you'll get an idea of what I mean. So I'm going to take a circle, and it's a pretty circle, and we'll center it at the origin. And what I want you to do is I'm going to trace this top half in blue. And so I'm going to say this is the equation y equals the square root. I'm going to use 9 minus x squared. And that's the equation of a semicircle, the top half at least. And if I label some points, for example, this is the point 3, 0. This is the point 0, 3. Oh. And if you want, for full disclosure, this is the point -3, 0. And so suppose I asked you to, for example, consider this shaded region. And I said, what's the area of this? Now, of course, if you paid attention in high school geometry, you'd rat off half the area of a circle. But let's assume we don't understand why that formula is even true. What would be the area of this? So the area of the blue region is the integral from -3 to 3 of this integral. So we see right away that even understanding the area of a circle, that formula you learned in school as a child, that pi r squared, if I would ask you right now to tell me why it's true, I doubt that you could. Well, after today's lecture, I suppose you can. Now, due to symmetry, it's even easier. We can multiply, we can just do a quarter of it. And so we multiply it by 2. Now, what I want you to think about is if I took a point on this circle, say I just took, I'll use a different color. I think about how I might want to integrate this, and I take some point here. And this is the point x, y. And so what I'd like to do is I would like to draw a perpendicular and then make this triangle. So we know this distance right here is x. We know the distance from here to here is y. We know the radius of this thing is 3. So if we just look at that triangle, let's pull this triangle out. We know by the Pythagorean theorem, for example, that x squared, excuse me, getting ahead of myself. That's x, and this is y, and this is 3. So what we know is we know that 9 is equal to x squared plus y squared. Now that is the Pythagorean theorem, but I can think of this in another way. If I throw an angle in here, if I give this a name, say theta, then another thing I can say is I can say, oh, okay, cool. So what is the sine of theta? Well, the sine of theta is y over 3. Another way of writing that is that 3 sine of theta is equal to y. And similarly, I can say 3 cosine of theta is x. So what I'm doing right now is, it might seem like I'm kind of doing all kinds of random things that there's no rhyme or reason, but that's actually not the case. What I'm doing is I am brainstorming. I am saying, okay, let's imagine I want to determine the area of the circle of radius 3. Well, knowing what I know about calculus and the definition of area from Calc 1, that means I have to integrate this creature right here. Or I can integrate this one and multiply it by 2. Now, what I already know is that I don't know how to integrate that, at least using what we've learned to this point. That square root is a problem. I'm not quite sure what I can do. I can't just set u to be what's inside. That won't work. One of those standard substitutions is not going to get the job done. And then I think about, well, the issue here is that this square root is posing a problem, and the only way to get rid of a square root is if what's inside is a perfect square. Well, 9 minus x squared ain't a perfect square. Or is it? It turns out it is, but we have to think of it creatively. So the first thing I would ask you to do is try to integrate that by setting u to be what's inside the square root. It's not going to work. But you should convince yourself it won't work. And so the thing we ask ourselves is, what will work, if anything? So what I'm doing is I'm saying, okay, let's look at, is there anything that's hidden in this problem? And I look at this picture. I draw a picture, because a picture's worth 1,000 words. You've heard that before. I draw this picture, and what stands out to me is that there's this subtle connection between the algebraic equation 9 equals x squared plus y squared and the trigonometric version of that. Because if I take this right here and this right here and plug them in here for x and y, what do I get? Well, a beautiful thing happens. Note, nine minus x squared is the same thing as, well, what's x? X is 3 cosine of theta squared. And so this becomes the square root of 9 minus 9 cosine squared of theta. So you're going to say right now, well, that's worse than what we started with. But it's not. Because what is that? If I factor out a 9, I'm left with 1 minus cosine squared times 9, which is 9. So what is 1 minus cosine squared? It's sine squared. Again, what am I using? I'm using the Pythagorean theorem. Or if you write it as sine squared plus cosine squared equals 1, we call it the Pythagorean identity. Now, this might look like a bunch of nonsense, but now we have written 9 minus x squared as a perfect square. So let's summarize. Before I switch pages, does anybody have a question about this? So if we go to the next page, what we just showed is that 9 minus x squared can be written as 9 times the sine squared of theta, which now is just 3 sine. So again, let's go back. So by using this sort of connection between x's and y's and angles, I eliminated the square root. Alternatively, I could have done something else. You know, if I would have called, if I go back a page, instead of using that angle, if I would use the other angle right here, if I use this angle, then I would have gotten a very similar statement. So alternatively, I could have done the following. So you can show 9 minus x squared equals 3 cosine of some other angle. Let's call it beta. So if I go back to the previous page, if I call this beta, so if I call this beta, then it just flips. It would be 3 cosine of beta is equal to x. Or, you know, did I say that right? Yeah. So the cosine of beta is x over 3, so it'd be 3 cosine beta is equal to x. Anyhow, if you do that, then you get this. So okay, so what are we supposed to take from this? Well, what this sort of little geometric investigation suggests is it suggests the following. So it suggests a new type of substitution. Replacing x with, say, the sine of theta, or x with the cosine of theta. So notice I'm being very careful with my words. I'm saying it suggests. Because as we saw with the substitutions before, the change of variables, it's not enough just to replace the variable. You also have to make sure you don't cheat with the differential, the dx. Does anybody have a question? So it turns out this is legal. And let's see exactly how it might work. So I start with my integral. Let's just worry about the antiderivative for now. So let's say we want to integrate 9 minus x squared. I'm not worried about the 2 in front. I'm not worried about bounds right now. We'll get to that in a second. So what I'm going to do is I am going to set, as we suggested, I'm going to set x equal to the sine of theta. And if I set x equal to the sine of theta, that's the same as dx being equal to the sine of theta, or excuse me, cosine of theta. D theta. So what does my integral become? My integral becomes the square root of 9 minus, excuse me, not sine. I got to go back. This is a slight typo. I forgot the 3. This should be 3 sine or 3 cosine. So if I set my x equal to 3 sine, and then this becomes 9 sine squared theta, and then my dx is replaced with 3 cosine theta d theta. Now, that 3 can come out front, and then inside my square root, we know we have 9 times 1 minus sine squared. And then I'm left with a cosine theta d theta out here. We know what happens to that square root. We already saw it simplifies to 3 cosine squared, square rooted. So this becomes 3 times 3 is 9. Well, let's guess we'll be even slower. Let's take our time. So this becomes 3 times, and then in here you have 3 cosine theta times cosine theta d theta. So the 3's become a 9, and now you're left with the integral of the type we talked about last week, a cosine squared, which of course you guys, we know we can write this as 1/2, 1 plus the cosine of 2 theta d theta. And this is not a very complicated integral. At least it shouldn't be for us at this point. Before we finish this problem, does anybody have a question? Okay. So there's a lot happening here. The first question you might have is you might say, why did you set x equal to 3 sine? Why not cosine? Well, I could have done either, but don't forget, if I choose x to be the cosine, then when I differentiate it, I get a minus sign floating around. The other question you might have is, when I took the square root of cosine squared, why is it just cosine? Couldn't it be negative? Yeah, that's a technicality, but it's not going to affect us in the problems that we're doing. What I mean by that is someone, if you wanted to be very particular, you could argue that this cosine needed absolute values. But we're not going to worry about that right now. It's not going to affect what we do. What we want you to, those little nuances, we will make sure they don't come into play when we do actual problems. Also, don't forget, the cosine is positive between negative pi over 2 and pi over 2, so that's not going to matter for our particular problem. Okay, how do we finish this problem? Well, we have to integrate it. So there's a lot happening here. The next step is that this is 9/2. Now, what's the integral? The integral of 1 is theta. Now, what was the next piece? The next piece was cosine of 2 theta. So how do you integrate that? That becomes 1/2 of the sine of 2 theta plus c. And so here is a point where you might also think we're done, but we're not. Because the original problem was in the x universe. Our variable was x, and we're not in x right now. We're in theta. So we need somehow to get back to x. And what we need to do in order to see where x comes into play is we need to draw our triangle again. So if I draw a triangle that illustrates my original substitution, what was my original substitution? It was x equals 3 sine of theta. So I can get that by putting a theta here. And sine of theta being x over 3 means this. And so another way of writing this is that x over 3 is the sine, and scarily enough, that the arc sine is theta, or the inverse sine. So I need this piece for the theta, and then what do I do about the sine of 2 theta? Well, that's going to be relying on some trig identities that maybe you don't remember. But you can simplify the sine of 2x. And it's called the double angle formula. So what we can do is this is 9/2 times the arc sine of x over 3, and then this is plus, using the double angle identity, sine of 2 theta just becomes sine of theta cos theta, and then this is over a 2 with a 2 out front, so the 2's cancel. A lot happening in this problem, by the way. Those 2's cancel. And finally, we can write the final answer, which is 9/2 the arc sine of x over 3. Now, what's sine of theta? Well, you already wrote it down there. It's x over 3. And what's the cosine of theta? The cosine of theta is the adjacent over x. So what's this adjacent angle? Well, by the Pythagorean theorem, it is, as you would guess, 9 minus x squared. So this becomes times the quantity 9 minus x squared. And that is your final answer in all its brutalness. Isn't that a beastly problem? Whew. So this is one of the more difficult integration techniques that are out there for students at this level. Yeah, so James, you're asking, you mean like formulas? There's absolutely formulas for these, sure. Yeah. So what James, you're referencing is what's called a table of integrals, which was very useful years ago. They're still useful before technology, but you know, now perhaps even easier would be to use software like Wolfram or any other calculator. So yeah, what you'll find in the back of the book is tables, and you could even Google search tables of integrals. But remember, one of the things don't get confused here. One of the things we want you to be able to do is understand where these tables and these formulas come from. This is brutal, though. It's a brutal problem. Does anybody have a question?
I have a question.
Yes.
So if this was a definite integral.
That's where we're headed next, because this is the problem you emailed me about, right? Well, not the same problem, but the idea, right?
Yes.
Yes. What was your question?
Would you always Sorry?
Now, are you asking about switching bounds?
Yes.
Yeah, so that's completely up to you. So I could have done this problem sort of, if we go back to the original problem, what we could do is we could have done it one of two ways. Now that we know the antiderivative, I can plug in 3 and then plug in 0 and subtract, and then I get the answer. Or alternatively, you could have switched your bounds from x to theta, and then you could have plugged your bounds into the top line. So that's personal preference. Does that make sense? So if you,
Yep.
let me reiterate that actually. If you would switch your bounds to theta, then you would use this guy. If you didn't switch your bounds, if you kept them in terms of x, you would plug them into the last equation. Yeah, I don't know if that makes sense or not, but that's one way to think about this. Does that make sense to you, Paul? Or?
Yep.
So, if you go to the back of your book, you'll see there's a table. And if you have your book handy, and I actually just opened it up, it's you can read this answer out of line 61 in the table of integrals. So, I mean, just if you wanted, you could clean this up. So you can multiply everything by 9/2. You get 9/2 arc sine of x over 3, and then the 9 kills the 9 over here, so you're just left with 1/2 x times 9 minus x squared plus c. So you could see these integrals are long and they're complicated. And most of these integrals that we'll give you to practice, almost all of them are going to simplify to the kind that we talked about last week with those powers of sines and cosines. That's why we brought those. We teach those because those are most, I mean, they're useful in their own right, but they often are what results when we do these trig substitutions. I've been teaching calculus for quite some time, and this is easily one of the most difficult topics. It just is. And some of you will say, all right, you'll have that mentality where you'll suffer to learn it. Others will just say, I'll miss that 10 points on the test, if it's on a test. But it likely will be. Let's go back to the original problem. So let's make sure it matches our intuition. So back to the original problem. We wanted to integrate this thing. 2 times the integral from 0 to 3 of 9 minus x squared in the square root dx. Well, what we just found is this is 2, and then I'm going to plug in, take that antiderivative. So it's going to be, we just found it. It's 9/2, right? The arc sine of x over 3 plus 1/2 x times 9 minus x squared. And then we're evaluating this from 0 to 3. So when you plug in 3, you get 9/2 the arc sine of 1. And then this piece goes away because whenever you plug 3 into the second term, it goes away. And then it's minus when you plug in 0, so it's minus 9/2 the arc sine of 0. And then, of course, 0 here as well. So one of the things that most students sort of don't remember or struggle with And one of the ways to think about these arc sines is I like to read them as the angle whose sine is. So this is the angle whose sine is 0, but that's just 0. And this is the angle whose sine is 1. Provided we didn't make any mistakes, of course. So what's the angle whose sine is 1? Well, there's lots of angles whose sines are 1, but if we imagine that x is between 0 and 3, the only logical solution would be that this is pi over 2. You plug pi over 2 into the sine, you get 1, right? It's the way to think about that. And so this becomes 2 times 9 over 2 times pi over 2, which simplifies to 9 pi over 2, which is what you would expect if you use your elementary formulas from geometry. The radius of our circle was 3. You square 3, you get 9 pi, but I took half of the circle. So that's half of the area of the full circle. So what we've actually just done, if you went and replaced everywhere you saw 9 with, everywhere you see a 3, if you replaced it with the letter A, and everywhere you see 9, you replace it with a squared, you've actually just proved the area of a circle is pi r squared. Does anybody have a question? Now, with anything, you're not going to learn this in 5 minutes, 10 minutes. You're not going to learn it watching me. You're going to learn it by lots of trial and error, and that's just what it is. When you do these problems, Paul, I'll call on you because you're the original one that asked the question. It's up to you how you want to handle those bounds. You can switch them or you can leave them. It's up to you. But you have to be careful and do it properly or you're going to get the wrong answer. Does anybody have a question? Now, if you wanted to, let's just look at that other way, Paul, so that we kind of make sure everybody's on the same page. If I go back a page, if I just integrate it in theta, I get this top expression, right? So alternatively, you could have done it that way. So alternatively, you could have done it like this. You can write this as 2. Now, we're going to switch our bounds in a second, but you know that this becomes 9 minus what substitution did we use? We used x equals 3 sine theta. So this is important for us. And then, of course, dx is 3 cosine theta. And so if you plug this in, you get this. Now, if I do my bounds, what are my new bounds? Well, this is probably what you're really getting out with your question, Phil. If when x is 0, what does that mean from this equation? Well, you get 0 equals sine of theta, and that implies that theta has to be what? What spits out 0? Well, 0 does. And then when x is 3, you need to solve 3 equals 3 sine theta, which implies, as you would probably expect, that sine equals pi over 2. Or excuse me, theta equals pi over 2. So that means my new bounds in terms of theta are 0 to pi over 2. And then, of course, if you go through those steps that we did before, what you arrive at is you arrive at what? Well, the antiderivative becomes this guy, 9/2, and then the theta business. So you have 2, and then you'd have the 9/2 times theta plus 1/2 sine of 2 theta. And you're evaluating that from 0 to pi over 2. That's a pi over 2, excuse me. And so this just becomes 9, and then you plug in pi over 2, so you're left with pi over 2 plus 1/2 the sine of pi. And then that's minus what happens when you plug in the 0, so you get 0 plus sine of 0. And those all go away. The only thing that survives is 9 pi over 2. Just to clarify this, the sine of pi is equal to 0. And the sine of 0 is equal to 0. So you get the same answer. I hope that helps clarify your situation, Paul. I'm not sure if it does, but hopefully that helps. All right, any questions about this? So the obvious thing is this is difficult to learn. This is tricky. But, you know, the other side of that coin is that this is a very useful strategy. And it's legal. It works. The details of why it's legal, we're not worrying about them in Calc 2. You could take higher level courses if you want to really know why it works. But it does work. And so we employ it when we can. All right, so here's some other things to consider when you get the next assignment. So, and I would encourage you to read the examples in the book because it's very important. So the above strategy works on many integrals. So here's a good way to think about it. So if you see something like a squared minus x squared, try exactly what we just did. Try x equals a sine of theta. If you see a squared plus x squared, you should try x equals a tangent of theta. What these allow us to do is they allow us to take advantage of different trig identities. And then if you see x squared minus a squared, you should try x equals the secant times A of theta. Notice my English here. I'm not saying that it works all the time. I'm not saying it's always the way to solve. I said, if you see, you might try this. But there might be an easier way too. And all this comes from basic right angles. Draw a right triangle and think about these relationships. Now, I guess I'm being very generic here. Make sure you understand that what I mean when I say if you see this, A is a number. X is the variable. That's the context there. I hope it's clear. And James, what you alluded to earlier, there's formulas for all these in the back of the book. You just have to know how to employ them properly. But it's also important that you know that I could ask you on the test to, I could say integrate one of these. And if I say, make sure you show the details or, without using a table, then you got to do it that way. That's part of the curriculum of this class, is understanding that. All right, does anybody have a question? Okay. If you guys don't have questions, I will remind you to keep working on those integrals. I'm gonna give another practice set that will ask us to work on these guys, and we'll give you some important ones, and then we'll move on. Any questions? Going once, going twice. All right, then. Well, thank you, guys. I will talk to you all hopefully on Thursday. And good luck with your homeworks and whatever else you're doing in life. Take care.